Welcome back. Another lecture on scale factor approach, where we would be using scale factor approach to obtain modeling and prediction rules for problems in thermal sciences, heat and mass transfer, for example. In the previous lectures, we had employed the force ratios to develop the invariant pi numbers. These are quite useful in the field of mechanics, but need to be supplemented when we deal with thermal quantities, especially when employing similitude in heat and mass transfer, two fields that famously employ similitude for quite a bit of work. It is pertinent to extend the method of similitude by use of scale factors for energy, energy flow, and mass fluxes. We will not deal with mass fluxes here, but we will deal with energy flow. With energy, as with force, the total number of forms occurring in all problems is unmanageably large. But it is seldom necessary to deal with all of these forms of energy simultaneously. The various modes of energy transfer that we'll use here pertain to heat transfer, conduction, convection, radiation, rate of heat storage in solids, and the rate of heat storage in fluid streams, transferring heat from or to solids. So let us consider them one by one. The rule applicable to conduction of solids is the Fourier Law. The rate of heat transfer Q dot is area times the heat flux, and the heat flux is given by the conductivity of solid K sub S times the temperature gradient d theta by dx. Fourier law of heat conduction. Converting this into a scale factor relation, we get KCS. Scale factor of conduction solids is KKS, scale factor for the thermal conductivity of solid, times K of length times K of temperature differences. As before, we note that it is not the temperature but the temperature differences that are relevant in the heat transfer problem. The resultant pi number is this. Conduction of fluid in solid boundaries. It is within the fluid. At the solid boundary, the heat is transferred through conduction alone because the velocity at the boundary is zero. So the applicable relation is still the Fourier law, except that the conductivity of the fluid is used, and d theta by dx is on the fluid side of the boundary. We get a similar pi number. The only difference is Ks is replaced by Kf, the conductivity of the fluid. The law governing the convection is the Newton's law of cooling. Q dot is area times H times delta theta, where H is the heat transfer coefficient. Delta theta is the temperature difference between the fluid and the solid boundary. So K of convection is Kh, KL square, K delta theta, and this is the relevant pi number. Radiation is written in terms of HR, the equivalent heat transfer coefficient for radiation, and we get a similar pi number. We will not deal with radiation in this course. Then the rate of heat storage in solids is the mass of the solid times specific heat times the rate of change of temperature. We call it the scale factor of unsteady temperature in the solid, and this is K rho KL cubed K CV specific heat, K delta theta, and KT minus 1, the time scale factor in the denominator. And this is the relevant pi number. Similarly, for the fluid stream, heat storage in the fluid stream, the mass flow rate is rho F AV, Cp is the specific heat, and delta T is a temperature difference. And so we get the heat storage in fluid stream scale factor having this pi number. This is using the laws to determine the pi numbers. We copied them here from the last table, and then we equate the scale factors for these. Then we get from this a pi number HL by Ks, heat transfer coefficient, times a characteristic length divided by the conductivity of solids. This is named Baer number and is abbreviated as capital B lowercase I Bi. If we equate the scale factor for conduction in fluid at the solid boundary with the rate of convection, then we get an equivalent formulation, HL by Kf, which is termed as Nusselt's number, where K is the conductivity of fluid. Note the difference between Baer number and Nusselt number. H and L are the same. The conductivity in Baer number is of the solid, and in the Nusselt number is for the fluid. If we equate the scale factors for conduction in fluid at solid boundaries with the heat storage in solids relevant to unsteady conduction for a solid immersed in a stream of fluid, the pi number that we get is L square by alpha tau, which is termed as Fourier number and abbreviated as FO, where alpha is Ks divided by rho Cv, thermal diffusivity. Ks and one more, convection and heat storage in the fluid stream. If we combine this, we get H divided by rho F Cpv as an invariant, and this pi number is termed as Stanton number, in which the rate of heat convection at the boundary is related to the heat storage capacity of the fluid stream. Let's do some examples in heat transfer. Is an example we did earlier using a different approach. Cooling of an infinite slab. An infinite slab of thickness 2L in the x direction is immersed in a fluid of temperature Tf. The initial temperature of the slab is T0 everywhere. the slab loses heat to the adjacent fluid, and the temperature profile changes. This temperature of the slab is coming down regularly, but it is highest at the center. It varies with x. This is the drop of temperature within the solid at a given moment, and this is the drop in temperature within the fluid at the boundary layer, thermal boundary layer, at the boundary of the slab within the fluid. The heat transfer rates involved here are conduction within the solid, and for this we had obtained the scale factor as K, Ks, Kl, K delta theta. Conduction within the solid and convection at the boundary. Q dot is like AQ, the heat flux, by the Newton's law of cooling. This is AH delta theta, which gives you K convection is KH, KL square, K delta theta. The two laws, the Fourier law and the Newton's law of cooling. There is a third law that is relevant: heat storage in solids. Q dot is the mass of the solid, Cv times the rate of change of temperature with time. This gives you this as the scale factor for unsteady changes in the slab. These three circled scale factors should be equal. That's the requirement of similarity. The three scale factors are given here. By equating the first two, I obtain the Bayer number HL by Ks, and by equating the first and third, I get Ks tau by rho CVL square, and using the thermal diffusivity alpha for Ks divided by rho Cv. This is alpha tau by L square, and this is named the Fourier number, Fo. So, the dependent parameter, normalized dependent parameter, which here would be T divided by T ref, reference temperature, divided by the characteristic temperature difference. The reference temperature is conveniently taken as the fluid temperature. So, this normalized dependent variable T minus Tf divided by the characteristic temperature difference T naught by Tf is a function of the normalized independent variable x star, the location within the slab, and two parameters, Bayer number and Fourier number. This is still quite complicated, and as was discussed earlier when we did this problem has been solved by writing this non-dimensional temperature difference dependent variable as a product of two factors. One, a factor where we determine this function at x star is equal to 0, and we multiply this by a correction factor which depends upon x star and Bayer number, hopefully. The first one is given by what is termed as the Heisler chart. Fourier number alpha tau by L square is given here. The non-dimensional temperature difference is here. And these are the curves for the different values of Bayer number, or as is written here, of 1 over Bayer number. This is the temperature at mid plane, T is at X star is equal to 0 at mid-plane, at the center of the slab. So for a given time, I can calculate the Fourier number. I can go up. I go to the relevant value of 1 over by number and read the non-dimensional temperature difference at mid-plane from this scale, the Heisler charts that you would have done in a course in conduction. These, of course, are corrected by the position correction chart. For different value of X star, the correction factor theta star divided by theta star at the midplane for various values of Bayer number. It's interesting to note that for very small values of Bayer number compared to 1, that is when 1 over Bayer number is large, all the curves for different values of X star or R star collapse into one line. That means there is very little temperature difference within the solid. The solid could be assumed to be at a relatively uniform temperature. And all the temperature difference occurs within the thermal boundary layers at the two boundaries. The case of low Bayer numbers, low internal resistance. Let's next do an interesting problem. A 1 kilogram roast of meat requires 60 minutes of cooking time in an oven. The chicken that is being roasted in an oven, it requires 60 minutes if the weight is 1 kilogram. How many hours would a 2 kilogram roast require at the same temperature? We assume geometrical similarity between the 1 kilogram model chicken and a 2 kilogram prototype chicken. If we normally cook a 1 kilogram roast and on a particular day we want to cook a 2 kilogram goal, how much longer should I bake? Okay. There are two laws that apply. Conduction in solids within the chicken meat, Fourier Law, and this is the relationship for the scale factors, and the heat storage within the solid. We assume the temperature at the surface is constant in either case, and this scale factor is given by this relation. Equating the two scale factors for heat flow rates, we get this relation which gives us the time scale factor as this. We can very reasonably assume that the density of the chicken meat, the specific heat of the chicken meat, and the conductivity of the chicken meat would be same. That is K rho, KCV, and K, Ks would be equal to 1. Scale factors for these quantities would be 1, being the same material. So this gives us Kt is like Kl square. The time scale factor is like square root of length scale factor. And what is length scale factor? Length scale factor is related to a mass scale factor. We are given mass, or we are given mass scale factors. Km is K rho Kl cubed, density times the volume, which gives Kl is like Km raised to power 1/3. So that Kt, the time to roast, should vary like K mass raised to power 2 by 3. Km here is 2 from 1 kilogram which we treat as model to 2 kilogram that we treat as prototype. So Km is 2. So that Kt is 1.59, and this implies that we would require 95 minutes instead of 60 minutes to cook twice the mass of the roast. 1.6 times about. Very interesting. Let's apply this law approach or the scale factor approach to problems in convection. In a heat convection problem, the motion of the fluid is also involved. This means that besides the pi numbers discussed above that related to thermal transfer rates, the pi numbers related to fluid motion should also be invariant in a convection problem. We had earlier obtained the following pi numbers related to fluid motion. We spent considerable time on these. Reynolds number RE, Euler number EU, and the Froude number FR. We had discussed that in problems where there are no free surfaces and where there is no cavitation involved, the Euler number and Froude number can be dropped and only Reynolds number matter. But if there is cavitation involved, then Euler number comes into play. And if the free surface of a liquid is there, then the Froude number comes into play. That is all we had discussed earlier in quite some details. There are many other pi numbers, but all are not relevant to a given problem. Let's consider force convection in which a stream of a fluid is passing past a hot object and is picking up heat from there. The stream is heated up and moves away, and this motion is forced. The following heat transfer mechanisms are involved: the heat conduction. The law is the Newton's law of cooling, which gives you this scale factor for the convective rate. Heat storage in a fluid stream. The fluid is picking up the heat and is getting heated up, so that we have for the heat storage in the fluid stream, this is the scale factor obtained earlier in this lecture. Equating the two, K convective and K fluid stream, we get Stanton number, that this is a relevant pi number. That should have the same value in the model as in the prototype. Rho F is the density of the fluid, Cf is the specific heat at constant pressure of the fluid, V is the velocity at which it is flowing, and H is the heat transfer coefficient. In addition, we need to model the fluid motion. The only relevant forces that control fluid motion are the inertial and viscous forces. Gravity forces do not need to be considered in the absence of free surface. The pressure forces also need not be considered because the cavitation is not involved, so Euler number is not important. We'd seen earlier that the pi number that ensures similarity of these two forces is the Reynolds number, Re, rho VL by mu characteristic. So that we can write Stanton number as a function of Reynolds number. Very simple relation. But convention makes things a little difficult. It is conventional these days to express results in terms of Nusselt's number. Nu is equal to HL by Kf, the conductivity of the fluid. It can be shown the Stanton number, which is H divided by rho F CPV, can be written as HL by Kf into mu by rho F LV times Kf by mu Cp. You can verify these cancels, L cancels. So this is H by rho F Cp and V, same thing as this. And what is this? This is Nusselt's number. This is 1 over Reynolds number, and this is 1 over Prandtl number. Mu Cp by K of the fluid is the Prandtl number of fluid. The Stanton number is nothing but Nusselt's number divided by Reynolds number times Prandtl number. Just another way of expressing the Nusselt's number. And if we do this, we can write Nusselt's number as a function of Reynolds number and Prandtl number. This is the relation that you use to write the correlations for various geometries in convective heat transfer, forced convective heat transfer in your course in heat transfer. For various geometries, how does the Nusselt number change with Reynolds number and Prandtl number? Let's do free convection. An object, heated object, sitting in an atmosphere with no draft because of the heat convection from the object. The density of the liquid changes. It becomes lighter. A buoyancy force acts on this and moves up and is replaced by colder fluid from below. This is termed as free convection. Forces causing the fluid flow: the inertia force, the viscous force, and in addition, the buoyancy force. The buoyancy force scale factor would depend upon the scale factor for gravity, the scale factor for density differences, delta rho, and volume, KL cubed. Now, K delta rho can be written as K rho times K beta times K delta T, where beta is the thermal expansion coefficient of a liquid. Beta is how does the density change with temperature. Matching the scale factors of buoyancy force with inertial force, which is K rho, KL square, KV square, we get this invariant. This is matching the scale factors of buoyancy force and the inertial force, J beta delta T L by V square. Thus, this Stanton number now is a function of Reynolds number in G beta delta T L by V square. The heat transfer portion is same, but now the fluid motion is governed by two factors, not just Reynolds number, but Reynolds number and G beta delta T L by V square. But there is no independent parameter V that can be used at the characteristic velocity. In fact, the resulting velocity is the result of the phenomena, result of the free convection. It is not something that can be specified independently. So since as a result, we can set Reynolds number to be order 1 so that it gives you an idea of what should be the characteristic velocity. If we set Reynolds number is equal to 1, the characteristic velocity should be like mu divided by rho L. With this parameter, which was obtained from equating the scale factor of inertial forces and the buoyancy forces, would becomes this. This is given the name Grashof number. It is abbreviated as GR. So the functional relationship can be written as Nusselt number is a function of Grashof number and Prandtl number. A very interesting result obtained with so little work. Of course, this can be improved if we write scale factors in terms of the direction, like we have done before. And it can be shown that Nusselt number varies like 1/4 power of the Grashof number. One last case study on free burning fires. Fires are very important for human existence. In fact, most of the history of early development of human civilization can be traced to the mastery of keeping the fires burning. A free burning fire is a cyclic process in which some of the heat generated by combustion is transmitted back to the fuel bed to produce combustible fuel, gaseous fuel, which then mixes with the air, reacts and liberates more heat. The combustion products are removed from the reaction zone by drawing in fresh air that further promotes combustion. Let's do a little study of this fire. The basic process of fire can be summarized as the generation of combustible fuel vapor from the fuel bed by heat supplied from the combustion zone. If we are using a fossil fuel like coal or even wood, then heating of the wood releases combustible gases. If we have a liquid fuel like a diesel or kerosene, then as it is heated, it vaporizes, and that vapor is combustible. Then vapor and oxygen react in the combustion zone at the elevated temperature to liberate heat. This heat forms a hot plume above the flame as the hot gaseous product are driven upward by buoyancy. And as this gaseous product move up, the cold air from all sides are drawn in and mixes with the flame, creating turbulent diffusion. A rather complex process for which the analysis is quite complex. Let's look at what are the forces that are important. Clearly, inertial forces and the gravitational forces through buoyancy are the dominant forces. Viscous forces can be neglected. Conduction is far slower than the mixing of gases involved here. Therefore, conduction can be neglected. Radiation too can be neglected. Relatively small energy in radiation. Only two laws need to be modeled. For the forces, inertial force, which gives you the standard form of KFI, and the buoyancy force, K delta rho, change in density times the volume times kg, gives you two pi numbers. And from this, if we equate the scale factor KFI and KFB, we get this pi number. For gases, delta rho by rho is like delta theta by theta. And the resulting pi number is like a Froude number. It's called a densimetric Froude number, or even Richardson number, Ri in literature. Now we want to conduct test on a small fire to model a large fire. One of the simple ways to conduct model test involves keeping delta theta by theta a constant. And if we can keep delta theta by theta as a constant, then Lg by V square is a constant. The temperature difference between a hot flame and the cold air, that is delta theta, depends largely on fuel type, the fuel configuration, and the cold air temperature. If the cold air temperature theta is the same, then using the same fuel and fuel configuration, we can show that delta theta by theta is a constant. And if that is so, then Lg by V square would be a constant. One of the phenomena that you see in open fires, which is burning freely, is the periodic pulsation. You look at this GIF, the fire bulges out and then sudden contraction and goes up and then this repeats. There is a periodic pulsation and there's a time period according to this. Now, if we do experiments in which we have kept delta theta by theta constant, then Lg by V square is a constant, and V square can be written as L square by tau square, where tau is the characteristic time. So that for constant delta by theta, this value of Richardson number reduces to Gt square by L as a constant between similar fires. Or that is, the time period is like L by G under root. Bryan and Nelson conducted experiments by using a liquid fuel on circular pans of different diameters from about 8 centimeter diameter to a meter in diameter, and they observed the pulsation period in seconds. And they get these dark points as a pulsation period versus pan diameter on the log-log scale. This red line is the line of the rule that we obtained earlier. So we see clearly that our modeling rule is quite valid. Thank you very much.